Hello everyone, I'm Vanilla, and today I'll be presenting about Transpolymer, a transformer-based language model for polymer property prediction. Why is this important? Traditionally, predicting polymer properties like conductivity and electric constant requires a lot of time, effort, and money. Polymers are complex. They can have different change lengths, balance, branching, and structures. So our objective is to use artificial intelligence, specifically transformer models, to make this process faster and more efficient. Literature review. Before diving into our solution, let's see what was already done. Traditionally, experiments and simulations were used. They are accurate but very expensive and slow. Later, machine learning models like CNNs, RNNs, and GNNs were tried. They worked for some cases, but they weren't powerful enough for polymers because polymers are more complex than small molecules. And this is where we saw the gap. There was almost no work using transformer models in polymer science. That's what motivated us. Proposed solution. Our solution is called Transpolymer. The idea is simple but powerful. First, we created a chemical aware tokenizer to break down polymer smiles sequence into meaningful parts. Next, we used a transformer encoder which self-attention to capture the complex relationships. Finally, we follow a pre-trained fine-tune approach. We, we pre-train on a large polymer data set using mass language modeling and then fine-tune on specific property prediction tasks. System architecture. Our system has four main parts: converting polymer structures into tokens, which is polymer tokenization; transpolymer framework, the overall design; transformula encoder, which is the core of our model; pre-training and fine-tuning, which is training first on a large data set and specializing for property prediction. Modules and tools. To implement this, we used Smiles representation for polymers, a chemically aware tokenizer to understand polymer descriptors, a Robert Terra style transformer as the backbone, libraries for PyTorch and RDKit for processing and arguing Smile data. Implementation. We pre-trained the model on about 5 million augmented polymer sequences from PI1M database. For pre-training, we use marked language modeling, like how BERT learns by guessing missing words. Our model learns by guessing missing chemical tokens. Then we fine-tuned it into 10 downstream datasets for predicting conductivity band gap, dielectric constant, and other properties. The results were very encouraging. Our model outperformed baselines like random forest, LSTM, and GNN. On average, it improved R square by 0.11 and reduced RMSE by about 8%. And most importantly, it worked well even with noisy and limited database. Challenges and solutions. Of course, we faced challenges. Data scarcity was solved with Smiles augmentation. Complex polymer structures were managed using chemical aware tokenizer. Overfitting was controlled with a pre-trained fine-tuned strategy. Finally, the conclusion and outlook. To conclude, this is the first transformer model designed specifically for polymers. It achieved state-of-the-art results across multiple benchmarks and proved that such models can generalize well for property prediction. Looking forward, we plan to extend the new polymer classes, combine transformer with graph-based models, integrate this into automated polymer discovery pipelines. This opens up exciting possibilities for materials science and engineering. Thank you.